So we finished off yesterday talking about the ultraviolet catastrophe, where basically. So let me explain a little bit more with this whole ultraviolet catastrophe and the reasons for it, because I don't think I fully explained myself well. So black body radiation. Okay, what we call a black body is what's called a perfect thermal conductor. It absorbs all energy, it emits all energy. Okay, which is why it's called a black body. Because the reason a black shirt feels warmer in the summer is because it absorbs all the frequencies of light, so it absorbs more energy. But at the same time, something that's black also emits energy very, very well. So if you have a car with black interior, it's going to get hot really quickly. But when you pull it into the garage, it's also going to cool down very quickly. Whereas something that is white will take longer to heat up, but it will cool down a lot slower. So a perfect black body is something that absorbs and emits everything perfectly. It doesn't actually exist. It's another theoretical thing, but that's what we call a black body. Yeah?
Why is like a shining white car just appear brighter than a shining blue car?
It's reflecting. That's it.
That's it.
Yeah. Most color is absorption and then emission. Shiny means reflect.
But white just does it better than you're saying?
Yeah. Well, white emits more of those frequencies. That's why it looks shiny. All right. Anyway, here's the problem, though. So we said heat is an electromagnetic wave, right? An electromagnetic wave's wave. So if you have this black body, there are only going to be certain wavelengths that will form a standing wave in this, we call it a cavity, in this oven, we'll say, right? So think of these heat waves, these infrared waves, this thermal energy. Think of it like springs in an oven. The oven's only so wide, so certain frequencies of springs will form standing waves. Everything else cancels out. The same way on the violin string. You with me? Problem is, as you get to shorter and shorter and shorter and shorter and shorter wavelengths, aren't there more and more and more sets that will fit inside that oven? So down by lower wavelengths, this works perfectly fine. But you get an infinite number of high frequency waves that will fit. And that was the problem, that there were all these different called modes, these different harmonics of these waves that would fit in, which basically meant there should be an infinite amount of ultraviolet energy in any black body. Quantization got rid of that because it said, okay, but look, these last 85% of your infinite energy, that's too low of a value. It can't possibly exist, and just cut that out. And all of a sudden, black body radiation worked really well. Okay? Now, it's important to note that Planck didn't come up with a quantum hypothesis to solve black body radiation, but it was accepted because it did solve. Okay? But the two weren't necessarily related. Does that make a little bit more sense? Or at least you guys are willing to smile and nod and continue along your way? Yes, this all works perfectly. All right. And so then we talked about that idea of a ramp. We don't experience these quantum effects in everyday life because that amount of energy is so small compared to what we can observe that it's like we live on a ramp. That ramp is just made up of an incredibly tiny staircase. Okay? And you guys got a younger sister, or maybe from when you were a kid, there's a dollhouse lying around your place? Yeah. Okay. Dollhouse with, maybe some of you don't have a little sister and still have a dollhouse lying around your place. I don't know. I don't judge. Mine was the Teenage Mutant Ninja Turtle sewer, but hey, that's just me. So you got those little staircases. If you try dragging, take a little block and try dragging it up your staircase at home, and then try dragging it up the staircase on the dollhouse, it's going to be a lot easier on the dollhouse, right? Because those steps are a lot narrower. So that's what I'm saying. It's because those steps are a lot smaller compared to you notice them less. And if you get much, much bigger, that might as well just be a ramp. Okay? So that's what I'm talking about with this whole ramp thing. Yeah?
So the y-axis is energy levels. What is
I'm not hitting anything. Nothing.
So it's
The stairs aren't a graph, they're an analogy.
Is it like a ladder? I don't know.
The stairs are just representing energy levels.
Okay.
Okay? There are no axes because it's not a graph or a visual representation of data or anything like that. It's just an analogy of the way quantum works is you can only jump steps when you have exactly the energy needed to jump a step. Okay? If you get extra energy, that's okay sometimes, but you're not going to jump 2 steps. You're going to take enough energy to jump the 1 step, and then whatever's left over can continue along its way. That's the idea. So you can't get too little energy and go part way. You can't get too much energy and go up 1 step and then another part. You can only accept energy that gets you exactly 1 step at a time. Okay? And that's it. All right, so 19405. So little historical background. There's a couple issues going on. All about light. Light is a bit of a controversial subject right now. Because the problem is, a lot of people like Huygens, Christian Huygens, who's a Danish physicist, a lot of people said light had to be a wave. And diffraction seemed to prove it, interference seemed to prove it, soap bubbles seemed to prove it. The fact that they had solved the luminous ether question seemed to have proven light is a wave. But then some other people came along, and Newton was actually one of these that said light can't be a wave, it's got to be a particle. And there was evidence for light is a particle. It's got to be. And so there was this debate going back and forth of what exactly light is. Enter in 1905, you got Einstein talking about something called the photoelectric effect. Here's what the photoelectric effect is. If you shine light at a metal, sometimes, if the frequency of light is correct, and if the metal's the right type, that light actually strips electrons off of the metal. So we got photons coming in here, they hit, some of those electrons bounce off. And so basically this is a method of making electricity. In fact, this is what a solar panel is. Okay? A solar cell is just light hits it, pulls electrons off, and you get current. That's all it is. Okay? Another example. Another example is you walk into a store, and as soon as your foot breaks some laser beam, you hear that really annoying ding-donging sound. Because you've got a laser impacting a plate, as long as that laser's impacting the plate, there's a circuit there, no bell goes off. But the second your leg breaks it, no current, a bell goes off. That's how those work. Same deal with if you've got one of those fancy garage doors that's got the laser across so that if you break the beam when the garage door is closing, the garage door shoots back up so you don't hit your car or crush your dog or something like that. But it's
When I was a little kid, I didn't know how those door, so I stood in front of the door and waved my hand, and listened to go dong 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 dong.
The fun thing about those garage doors, and by fun I mean annoying, is when you've got to close the garage door from the inside, but you need to be on the outside, so you have to hit it, and then run. You have to pretend you're a ninja and do the leaping, twisting kick in midair, and you look like an idiot. And then inevitably you land on your face, and some neighbor kid is across the street, and then you hear about it at school the next day, and you just get sad.
That's a bad example.
Actually, no, I'm just making this up. What's up?
Well, I was going to say, I've gone through my garage door like that several times. I've never done it in the way you just described.
Well, not all garage doors do.
Yeah,
No, mine
has
has
the
to-
sensors. I
you
don't
have to get
ninja
into-
kick though. I just step over
Like,
it.
if you have one in the garage door, it goes up if you cross it, so.
No, I'm talking about, that's what the one I have. I just never did it.
I had to do it.
See, at least when I grew up, the laser was this far off the ground.
Oh.
So if you just ran, it didn't work. So you had to leap it.
Yeah, that's how mine is.
Yeah.
Awesome.
Yeah.
Oh,
Get that forward somersault going on. It's like an obstacle course. And then you were a little too slow, and so you jumped a little too high, clocked your head into the garage door, and landed on your back. That one might have happened. What's up?
Was there ever a way to see the laser or a box thing? Because when we were little, we thought there was a garage door like that, and so we just stood there and let it close. But my brother almost died, and I had to pull him through, and it was a terrible experience. But is there a way to a box?
Two ways. Number one is if you see the box down by the ground, that would be a pretty good hint. But actually, you can see lasers if you take like hairspray, and actually I'm going to do this tomorrow with some fog. But if you take like hairspray and you squirt it, you will actually see the laser beam. Hairspray or anything aerosol works great. Febreze is fantastic for it.
You just turn the lights off.
So, like, last year, actually, at a point, I was going home and my sister was closing the door and she didn't see me walking down because she had gotten a ride or whatever. On my way, the door was closing, so I ran to try and put my foot in front of it to break the beam so that the door would go back up. But I was my foot was a little bit too low and it closed down on my foot, and it took me about 5 minutes to get my foot out from underneath that.
Did stop.
I like how this class has turned into garage door horror stories. What's up?
Do those alarms exist? Like, you see in the movies where they're trying to go around the lasers and stuff?
Sure.
No, those lasers cut through. They don't set off.
Laser beam trigger, sure. Through the exact same principle as the sensors at department stores, letting people know that there's a customer. It's the exact same principle, just one has an audible alarm, one doesn't.
So there's just lasers shooting everywhere.
You can. I mean, it's not all that effective, but you could. What's up?
I never understood that, why they always have them in different directions. Why not just have a straight line of lasers so you can't...
I don't know. I'm not a security expert. My guess would be Hollywood.
Yeah.
That's usually my answer for everything. All right. Yeah.
You know, like for barcodes,
Uh-huh.
there's two types of, like, there's one that's just one straight line, and the other is just a mishmash of.
QR codes versus barcodes, yeah.
How does that?
Actually, we should have talked about that when we talked about diffraction. Basically, the idea is... Oh, we never talked about how CDs work either. So let's talk about those two things real quick. So barcodes are basically you shine the laser, and because the laser hits the edge of the ink on the barcode, it creates a diffraction pattern. It acts as a single slit interference. And so that diffraction pattern basically will form a pattern that the barcode reader reads that says bright, dark, bright, dark, bright, dark, bright, dark, where bright is ones, dark is zeros. And so you get that message in ones and zeros that the computer can understand, and you're done. Same thing with DVDs. The way DVDs work is when you burn a DVD, you are literally cutting grooves into the DVD. And the DVD reads it by having the laser shine at it and spin. And when the laser hits a groove, it acts as double slit interference, and you get a diffraction pattern, which corresponds to ones and zeros that the computer can read. Yeah?
What about rewritable DVDs?
I don't know. I think those just have a whole bunch of layers that you can burn. And when you rewrite, you burn off the old layer, and then you just burn into the new one. I think. I don't know exactly on those. But I will say, the only difference between DVD players and Blu-ray players is instead of a red laser, Blu-ray players use a blue laser. That's the only difference. Because a shorter wavelength means your slits, your diffraction gratings, if you will, can be closer together, which means you can store more data on the disc because you're reading it with a smaller wavelength. That's also why if you ever hold up a DVD and a Blu-ray, you can almost see through the Blu-ray because there are that many more cuts into the disc to be able to read the data. That's how that stuff works. Yeah?
Can you personally see the difference between regular HD and Blu-ray? I can't see it.
I can a little bit, I just don't care.
Exactly. I might if I like.
Blu-ray ruins animated movies.
It takes time getting used to the sign screen resolution.
Like I was watching Toy Story, I think, on like Blu-ray player at Sam's Club or something. It was so disappointing because it didn't look right.
Alright. And moving on from consumer advice.
I do have a question about
Yeah.
TVs, though.
Oh God, what's up?
Somebody said that if you rub it with like ketchup, it'll take care of the scratches.
I thought it was banana.
Yeah, or like peanut butter.
No, it's like the iron in the ketchup, or not iron. Something.
I thought it was
I tried it.
It just smooths it out while it like fills in the scratches.
Then my hands just smell like ketchup.
Yeah, see, I'm not sure on that
And
one.
then you see- I heard
Oh
the
no,
same thing about
maybe.
bananas.
Maybe not.
Think of banana.
Alright.
I would always say banana.
How about if it's a CD? CDs are cheap, just go get a new one at that point.
Well,
But a
if it's a
DVD, like-
$60
Like
video
if you
game
get it,
disc,
if you
I
rent it,
can't.
you
I'm not gonna
Oh
go
right,
back.
people still buy computer game discs. Alright.
Who does that?
Did I say
Alright.
That's a video game.
Xbox, they use the disc.
Don't have to.
Why do
Yeah,
they
you
use
can.
it?
You can get it online.
Anyway,
I don't ever.
photoelectric effect.
I still buy my stuff.
Oh no, I still buy it. I just
Yeah, I
don't
buy
buy
all
the
the
DVDs.
You just download it.
I just download it onto the. I prefer everything electronic because
It's better that way.
I have 2 cats. Nothing physical will survive long. Yeah. All right.
I'm sorry.
Photoelectric effect. So here's the thing. Photoelectric effect winds up a bit as a showdown. Okay? Photoelectric effect winds up as a, okay, here's what the wave theory says. Here's what the particle theory says. And you know what? We can easily tell the difference of what's going on here. Because there isn't a, oh, well, maybe the particle theory could do this, but maybe it looks more wave-like because something like this. There is a clear experiment, a clear set of data that can be run, that can be done to show, once and for all, wave or particle, friend or foe. So,
That was a fun Spider-Man game.
we're going to kind of run through a little bit of the justifications here. So here's what the wave theory says. What the wave theory says is what's ripping these electrons off of the metal is the amplitude of the wave. Basically, the wave hits when it's at a node, and that antinode of the wave kind of pulls the electron off with it. So according to the wave theory, if you increase the intensity of light, you're increasing the amplitude. So more electrons should be ripped off, and they should be ripped off going faster. Okay? So according to the wave theory, the frequency doesn't matter. Because how quickly it's going back and forth doesn't matter. It's how far off of this plate they're ejecting the electrons. That's what matters. What's up, Andrew?
I'm good. I'm
All right, that's what the wave nature says. That's the wave camp. Any questions on that? Think of it as if I took that big slinky, okay, and at the bottom I had someone grab hold, and then they kind of rode it up to the top. The higher up that goes, the faster they're going to be going, because the higher I had to fling them, the faster I had to make them. So the higher that amplitude, the quicker it's going to fling off the electrons. That's what wave theory says. Particle theory says what's going on here is that we have these particles of light. Originally they were called corpuscles, which just sounds weird, but it comes out of Latin, because everything came out of Latin. We now call them photons.
Is that where they're corpuscular?
Yes.
Okay.
So now we call them photons. So these photons impact the electrons. And when they impact, it's a collision. So if the impact imparts more energy, or imparts, we'll say energy, imparts more energy than the metal can hold on to the electron with, the electron goes off. Well, what did we say about the frequency of light? E equals hf. The higher the frequency, the more energy it has. So the higher the frequency, the more, the higher the frequency, the more energy these electrons should get because they're involved in a more energetic collision. Make sense? So the frequency is what should determine the kinetic energy. All intensity should do, well, if there's a higher intensity, aren't there more photons? And if there's more photons, then there should be more collisions. So you should get more electrons, but they should all be at the same energy level. So frequency will determine the kinetic energy. The number of photons will determine how many electrons. That's what particle says. Does that make sense? Maybe kind of, sort of? Look, we're talking about the difference between launching somebody. Let's say I have you guys all stand in a line. Okay? No, I'm not going to have you actually do it. But I have you stand in a line. And I'm going to stand here. And I'm going to do something that's going to launch you out that way. Okay? Wave theory says essentially I'm sitting here spinning. And as I go around, I grab your arm and fling you. So if I make my arms longer, if I hold a stick out, there's a longer arm and I'm going to throw you further. Particle theory says I get a bunch of football players to come slam into you. The more energy they slam into you, the further that way you go. That's the difference. So they do this experiment. They do a bunch of times. Millikan pops up again because that's just what Millikan does. But what we get is this graph here. frequency versus wave, kinetic energy versus frequency, and we get lines that look like this. So here's the thing. We're going to go into more detail about the photoelectric effect later, probably tomorrow. This is a graph that if I say draw a graph of the photoelectric effect, you should be able to do from memory. You need to be able to do this graph. So here's what you got. Kinetic energy, frequency. When you actually start doing that, each of these lines is a different metal. So notice they are all parallel lines, because it turns out, and this is handy for the fact that our equation is E equals HF, it turns out the slope of the line of a photoelectric effect graph has always turned out to be Planck's constant, H. Always, always, forever and ever. So our equation for photoelectric effect looks pretty similar. It's kinetic energy, E, equals HF. But we have this W naught term. Now, you will also see this term as a phi, a circle with a vertical line through it. People write it both ways. AP kind of varies on which way they choose to represent it. So the energy is equal to the energy of the photon minus what's called the work function. The work function is how tightly this metal holds onto the electrons. So you need a minimum frequency, what's called a cutoff frequency, in order to even eject these electrons. But after that, it increases linear with the slope of h. So based on this data, which camp won?
What?
Based on this graph. I gave you kind of the rundown of what they said the two different camps would say. Which camp won? Particle. Because particle said the kinetic energy should be based on the frequency. Wave said the frequency shouldn't matter. This should be based completely on intensity, on amplitude. Particle won.
Wait.
Can I explain what?
You said particle 1, right?
Yes. Yeah, I'll get it. Because particle said the higher the frequency, the more energy a photon has. Okay? So if it hits with more energy, it should give the electron more energy.
So as E max increases, it also.
Yes. So because your kinetic energy is a function of frequency, that meant light had to be a particle. All right? Questions on this? Beautiful. So now we change light from waves into this concept of photons. And photons have a couple handy little things. Namely, they don't have mass, which is why photons can travel at the speed of light. Can. They are pure energy. So, all the time. So, photons don't have mass, so traveling at the speed of light isn't a problem. Because while your mass increases an infinite amount, if you have no mass to begin with, 0 times anything is still 0. The energy a photon has is based off the frequency of light. And this is an equation we've already gotten. The energy of a photon is equal to h times f. Remember, h is Planck's constant. What is Planck's constant equal?
6.26 times 10 to the negative 34.
6.626 times 10 to the negative 34th.
34?
Yeah, it's a small number. Now, we also have momentum. A beam of light has momentum. Except what two things do you need to have momentum?
Mass.
And velocity. Well, sure, a photon can have velocity. Its velocity is the speed of light. But it doesn't have mass. Except don't forget, mass is also equivalent to energy. So light does have a mass. It is an equivalent mass based on its energy. And so instead of saying the momentum of light is equal to mv, we have to say that the momentum of light is equal to h divided by lambda. H again being Planck's constant, lambda being the wavelength of that light. So I'm going to prove that real quick. Because I can. I feel like it. I wish I brought my blue laser today. I left that at home. That's unfortunate. This is problematic. My radio scope disappeared.
This one uses laser beam for demonstration.
Huh. Give me 1 second, guys. Sorry about this.
Failed tremendously. This is why I am now utilizing Operation H. I'm going to put my laser beam on the moon of the Death Star.
It's really distracting.
Ashton Powers will never defeat me now that I've stolen his mojo. I didn't realize what they were extracting from it first, and now that I watched the movie, I get it, and it horrifies me.
I need to watch it again. My brother and I were going to, but then he had a kid.
I've only seen the third Austin Powers movie.
You need to see it.
Oh, you know what?
No, I think the best line of the trilogy was at the start of the second movie. My wife was at Bandolph this entire time. Wait a tick, that means I'm single again.
You know what this movie needs? It needs more mojo.
Who needs swag when you've got
You okay, Andrew?
Okay, Brett?
That's not my Swedish made penis and Roger. I swear.
Dr. Idle, can I paint the woohoo's gold now? Hey, sweetie, do you have a little clone in you?
Huh.
Do you want some?
So, like, no one had really stupid
Your
conversations
spy
going
calls
on that
it
I'm going to
mini.
regret hearing on the recording, right?
It's not the size.
Hey, computer. Hey, honey, do you have a little clone in you? Yeah, no, I don't. Do you want?
Huh. All right. I'm going to have to track down what happened to that.
Austin Powers, actually.
Oh, that's unfortunate. All right, so I'm going to have to save the solar sail demo for tomorrow, I guess.
because you don't have mojo.
All right. So I'll have to prove that tomorrow. What? Yeah, I got a bunch of demos tomorrow.
Compton effect.
All right. So now we get the Compton effect,
Straight out of Compton effect.
which is not straight out of Compton, it turns out. In fact, the video I'm about to show you is as far from straight out of Compton as you can get.
Space.
It is actually, dorky. It's a video a couple physics majors put together. No, that video disappeared. All right, I'm gonna have to. I'll have to show you later. Okay, Compton effect is basically this. Apparently, everything's disappearing today. Compton effect is this. If you shine X-rays at a block of lead, some of those X-rays are going to reflect. And it turns out when those X-rays, or those gamma rays they sometimes use, hit and reflect, the wavelength changes. And the only way wavelength could change is if this was actually a wave and not a photon. If it's a photon, it should either get absorbed or knock something loose. For it to hit and its energy to change is basically saying, okay, well then this is actually a wave. It's kind of weird. Hold on, let me see if I can get that video on
The YouTube.
Not the YouTube, but let's see on my actual computer. I think for some reason the videos haven't transferred over to my laptop, which is weird, but okay.
Good news, everyone.
You're now reading this in my voice.
Alright, yeah, for some reason it's just not working on my laptop, so we'll just watch it here. This is impressively dorky.
Let's do it.
When you go to your contacts, you just say black.
2,000.
Just go to the contact and say black.
Oh, hi. Yeah, I'm gonna do my workout. You know what else I like to do in my free time?
This guy reminds me of Justin, actually.
That brings me to this lovely experience right here. In 1923, Arthur Compton
It does.
argued that if light is quantized, then one can observe that scattered gamma rays will have a longer, greater wavelength than the incident ones. This is based on the idea that if photons have energy, they should also carry momentum, and as such, they should undergo scattering collisions just like a particle. An example. This is an electron. Here you have a gamma ray coming in at an incident wavelength. It collides and scatters just like a particle would at some greater wavelength. Now let's go into our experimental apparatus here. We can see that contained within this lead unit, we have a cesium-137 source, highly radioactive. You don't want to remove this because it might hurt you. There's an aperture here that collimates it into an aluminum rod, much like this one here. Now aluminum is good because it has a lot of extra electrons in its valence band that can be ejected. Those are then projected onto this scintillator, which detects anytime a gamma ray hits it. Now that produces a voltage pulse. That voltage pulse is then channeled into an amplifier, and that amplifier then produces a signal, which we can see on our oscilloscope, as well as being recorded on our multi-channel analyzer for data acquisition later.
Okay, so as Jeremiah said, we get voltage pulses from our scintillator here that go through the amplifier. And what we have to do first, before we can actually take any data, is...
Alright, we're going to skip past the calibration and all that stuff.
Put it in front of the source.
I don't know why. Actually, this is a pretty nice lab, but that's kind of sad.
Keep that. And after we've done that, we heavy lead frets back on here.
I like it when he speaks rather than.
They're going to lose a little bit.
Yeah, what's the right?
What is all this?
What's up?
It's not even me.
Huh?
Yeah.
I don't know.
Just energy of the scatter bit, energy versus the number of hits we get go down.
So basically the idea is light hits, it scatters at a different wavelength, which shows it has momentum. Except it also indicates that light is actually a wave, which is annoying because we had just settled this argument, 5 years ago with photoelectric effect. It's the equivalent of two small children, bickering for 20 minutes, and finally the parent yells at them, and then 5 minutes later they start going at it again. It's annoying. Light's a particle. Deal with it. Maybe not with Compton effect. So let me move along. This is one of them. I'm gonna give you more details about Compton effect experiment later on.
I can see it.
He's got the hair.
All right. Now, this is also kind of weird because something else starts happening. What's called photon interactions or virtual pair production. Basically, occasionally when a photon hits an electron during photoelectric effect, that photon disappears. Sometimes. It just goes away for a while. And then sometimes it shows back up later on. Just goes on vacation. Didn't know why. Photon hits electron, electron disappears. I'm sorry. Photon hits electron, photon disappears, and then sometimes even minutes later, all of a sudden the photon shows up again. It's weird. There's really no reason for it, at least not that we knew. On top of that, occasionally a photon will spontaneously turn into matter. a photon can turn into an electron and a positron. People who were there yesterday will remember that a positron is what?
Dark matter.
The antimatter version of an electron. So what happens when the two collide? Boom! So the photon turns into an electron and positron. 99.999% of the time, they collide and they go boom and turn back into energy photons. No big deal. Except, what's up?
Could they also turn into something other than photons when they are converting into energy? Could they be like gamma rays?
Well, that is a photon. A photon is any electromagnetic, whatever. I mean, light, gamma rays are light. They're just very high frequency light. Anything along that electromagnetic spectrum we consider a photon. Radio waves are very low energy photons. Here's where things get funky though. This is the one little side track onto black holes that I will make. Until we talk about them more later on. Sometimes this can happen at, like, say, the edge of an event horizon, where the photon turns into an electron and positron, and sometimes the electron is on one side of the event horizon and the positron is on the other. So the electron gets sucked in, the positron shoots away, or vice versa. And all of a sudden you have matter spontaneously being created out of energy on its own, randomly in the universe. As a quick aside, this is also why black holes evaporate. But that's neither here nor there. Yeah, if you weren't aware of it, black holes evaporate.
Always.
Yeah.
Hawking radiation.
Yeah. Black holes must evaporate. Now, the last black hole will evaporate trillions of years after the universe has died. It's a very slow process, but black holes evaporate. It's why if the LHC had actually created miniature black holes, no one was actually concerned about it because they would evaporate so quickly that they would never have time to do anything. Because if they're that small and evaporation is proportional to the area of the event horizon and blah, 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 blah. All right. Oh. So here's the problem. We've got a bunch of experiments that show light must be a wave. And it behaves like a wave. We've got a bunch of experiments that say light must be a particle. And it behaves like a particle. We still don't know what light is. Light is weird. It turns out it's not just light that's weird. But we'll get there.
Which one must be?
Well, some of you are more weird than others. So here's the thing. Collectively, here's what the community of science has decided to say. Light can be whatever it wants to be.
Don't judge light for its choices.
Light is a wave. Light is also a particle. Sometimes it's one, sometimes it's other. Sometimes it just randomly switches and jumps back and forth between them. We don't know. Sometimes light behaves like a wave. Sometimes it behaves like a particle. It is both, and we call that wave-particle duality.
Can it behave like both at the same?
That's the one exception that I'm getting to. Okay? This is also known as, the word I have never been able to pronounce in the 6 years I've been teaching this, the principle of complementarity.
Complementary?
No.
That's not...
Complementary.
Yeah, complementarily. Yeah, see what I mean by that? That's a hard word to pronounce. But the basic idea behind it is light can be whatever you need it to be. Which sounds like really cheesy and like something out of a really bad like romantic comedy. But that's what it is. If you need an experiment that only works if light is a wave, light's a wave. If you're doing an experiment that only works when light is a particle, it's a particle. The thing is, light cannot be both at the same time. If you try doing an experiment that requires, like let's say you do a photoelectric effect, which requires light to be a photon. But you do the photoelectric effect, you get the energy from the photoelectric effect by first shining a laser through double slits, which requires light to be a wave. One of the two will fail. Either you will not get an interference pattern from the double slit experiment, or you will not get electrons ejected from the photoelectric effect. It can be one or the other, never both.
And that's the thing I was asking about for the beginning of the year.
What? I don't remember what you're asking.
Like it'll go through the slits, and then sometimes it'll be a wave. It like depends on.
Yeah, we're actually gonna get more in depth than that. That it gets weirder. Yeah.
So, is it just random which one it is? If it
No, it's very specific. Like every time you do the double slit experiment, it will behave like a
So
wave.
I'm saying, like, if you did the double split and then you needed that.
Honestly, I don't remember.
Other thing. Okay.
I don't remember. I think it's whichever goes first, I believe, but I honestly can't remember. So wave particle duality. They're both. You know what? And I think that is an excellent place to hang up for now.
Is this de Broglie?
This is de Broglie. I feel like de